Hello there, Mr. Sutton here, bringing you the Algebra 2, Chapter 8 Quiz Review Solutions on Probability. For this question, we're randomly drawing a marble out of a bag containing all these different types of marbles, and we want the probability of drawing a marble that is not red. So given that there's a few red marbles and a bunch that are not red, it might be just easier to figure out the probability of a red marble, and then just subtract that from 1. Use the complement. So how many marbles are there overall in here? We've got 5 plus 9 plus 3 plus 16. So that's 14, 17, 33 total. So the probability of a red marble would be something over 33. Now there's 9 red marbles, so 9 over 33. And then we might as well just reduce that at this point. We can reduce this by 3's to 3 over 11. But now we wanted the probability of not red, so we'll just do 1 minus 3 over 11. And that's going to be 11 over 11 minus 3 over 11, so that is 8/11ths. For this problem, we roll a 6-sided die 60 times and record the results down here. We want the experimental probability of rolling a 2. Okay, well, there's 60 total trials. And out of all of those, we rolled a 2, it looks like 14 times. So we just have to reduce that. So we can reduce this at least by 2's. That would be 7 over 30. On this one, we have a two-way table showing the results of a survey asking students whether they play a sport or musical instrument. They want us to make a two-way table that shows the joint and marginal relative frequencies of all this. All right, so in order to make this happen, we're basically going to figure out what all these add up to and then divide all of these by the total to get some percentages. So let's add all these together. 46, 61, 64, and 79. Let me go to Desmos for that because I don't want to mess this up. So we got 46, 61, 64, and 79 getting added together. That's a total of 250. So now we're going to go through and divide each of these by 250, and then we'll also figure out the marginal relative frequencies. So I've set up another kind of table here, but I've left room along the margins horizontally and vertically to get those marginal ones. Just for a point of reference, the joint relative frequencies are just the original 4 here, and we're just dividing all of those by 250, and then we'll add those together to get the marginal frequencies. So let's just go left, right, top to bottom. So we were doing 46 divided by 250. So let me go down here. 46 divided by 250 is 0.184. And then we've got 61 over 250. So let me just change that 46 to a 61. That's 0.244. Next, we'll do 64 divided by 250. So that's going to be, let's see, 0.256. And then we have 79 divided by, you guessed it, 250. And that's 0.316. Now, if you've done this correctly, these all should add up to a grand total of 1. And we'll see that as we do the marginal relative frequencies. So let me do the ones on the right side first here. So we do 0.184 plus 0.244. So 0.184, 0.244, and that comes out to 0.428. And next up, we've got, let's just change that up, 0.256 plus 0.316 is 0.572. And if you do a little quick addition, you should get these to add up to 1. Let's add vertically now. So we've got 0.184 plus 0.256. So 0.184 plus 0.256 comes out to 0.44. And then over here, I'm expecting this to be 0.56, but let's just make sure. 0.244 plus 0.316 is 0.56. And if we add these either horizontally or vertically, either way it should come out to 1. On this problem, the marketing manager of a store surveys people in 3 different cities, and the survey asks whether they would shop at the store. The results are given as joint relative frequencies. It could be given as raw numbers or joint relative frequencies. It actually won't affect our final answer. They want us to now find the probability that a person would say yes, given that they are in city C. Now you got to be careful with the formatting of this language here. They're not just asking for yes and they're in city C. They're saying, assuming that they were in city C, what would they say? So it's a conditional probability type of question. We are looking for yes, given that C has already happened. So in order to figure this out, we need to do the probability of yes and C divided by the probability of C. Basically, what percentage of the people who do live in city C actually would say yes. So we're considering this very narrow piece of it here. So we've got yes and C, that's going to be 0.15. And then city C, the probability of living there is just 0.15 plus 0.19. So let's run those numbers on the calculator. So fraction 0.15 over 0.15 plus 0.19 comes out to about 0.441. So there is a 44.1% chance that somebody who lives in city C would say yes and shop at the store. For this problem, we flip a coin and use a random number generator to generate a number from 1 to 10. What's the probability the coin shows heads and the number is 2? So since we're looking for an and kind of statement here, that means we have to think about, are these two events independent or dependent? Well, flipping a coin doesn't change your random number generator at all. It doesn't change what it can generate. So these are independent events. They don't affect each other's sample spaces. So we're going to figure them out individually and then multiply the probabilities together. So let's use our normal independent formula, just P of A times P of B. And just to label some things, A is the probability of heads, and let's let B be the number, the probability of getting 2. So we've got the probability of heads, that's just 1/2. And now the probability of getting a 2 out of this generator, since you have 10 total possible outcomes and 2 is just one of them, we have 1/10 there. So we're doing 1/2 times 1/10, which comes out to 1/20. On this problem, we have a bag containing 9 yellow marbles and 5 red marbles. We randomly pick 2 marbles from the bag. What's the probability both are yellow when you do not replace the first marble before selecting the second marble? So we're looking for the probability of yellow and yellow. Since it's an and sort of probability, we need to think about independent versus dependent. Since I'm not putting the marbles back, what I get on the first draw is going to affect what I can get on the second draw. At the very least, it'll affect how many marbles there are to choose from. It also might affect the ones that I'm looking for. So this is a dependent situation, which means our formula we're using, P of A and B, we're going to have P of A times P of B given that A has already happened. So we need conditional probability of B given A. So for our events, A is the yellow the first time around, and B is also yellow. So the probability of that first yellow, we have 9 yellow marbles out of a total of 14, and we can't really reduce that, so we'll just leave that the way it is. Now the probability of a yellow, given that a yellow has already happened, so P given A, since we already picked a yellow the first time around, that means instead of 9, now we're down to 8 yellow marbles that we have to choose from. And we lost 1 marble overall, so this 14 now is reduced to 13. And we're just going to multiply these together, 9/14 times 8 over 13. And if we want, we could reduce this a little bit. So 8 over 14, that can reduce to, let's see here, this could be a 4, this could be a 7. So 9 times 4 would be 36. 7 times 13 would be 91. So 36 over 91 for this one. On this problem, we've got some more marbles. So we have a bag containing 5 reds, 3 blues, and 5 yellows. We randomly pick one. We want the probability the marble is red or blue. Since we're talking about or, we have to think about, is this a disjoint or overlapping sort of situation? So there are no red marbles that are also blue. They're two completely different groups. So this is disjoint, which means for our formula, we can just do P of A plus P of B. We don't have to subtract any overlap. So A in this case would be the red marbles. B would be the probability of the blue ones. Probability of a red marble is just 5 over, let's see, there's a total of 13 here. Probability of blue, we've got 3 over 13. And now just adding those together, 5/13 plus 3/13 gives us 8 over 13. On this problem, we have some chocolate going on, a box of chocolates with 7 milk chocolates and 5 dark chocolates. 2 of the milk chocolates and 4 of the dark chocolates have peanuts inside. You randomly select and eat a chocolate. Hopefully you don't have any allergies if you're just randomly doing this. Find the probability it is a dark chocolate or has no peanuts inside. All right, so is there any overlap between dark chocolate and no peanuts? They said there was 5 dark chocolates and 4 of those dark chocolates have peanuts. That means 1 doesn't. So there is some overlap between no peanuts and dark chocolates. So this is overlapping. We're going to use the overlapping formula, P of A plus P of B minus P of A and B. Let's let A represent dark chocolate, and let's let B represent no peanuts. So probability of dark chocolate, let's start there. Well, there's 5 dark chocolates out of a total of 12 there if we add those together. So 5/12. Now let's also figure out no peanuts. So they said, let's see, 2 of the milk chocolates and 4 of the dark chocolates have peanuts. That means there's another 6 out of the original 12 that don't have peanuts. So 6 out of 12. And I'm going to leave that as 6 out of 12, not reduce it, because I know I'm going to have to add this together later on with some other fractions. Now let's look at P of A and B. These would be the dark chocolates that have no peanuts. And again, there's 5 dark chocolates and 4 have peanuts, so 1 doesn't. So that's a 1 out of 12 probability that we meet both of these conditions. So putting all that together, we've got 5/12 plus 6/12 minus 1/12. That is 11/12 minus 1/12, which is 10/12. And if we want, we can reduce that to 5 over 6.